if I have a solution of my equation or a state of this ring of fire at a given instant in time, and if my equation of motions are such so this is now the rate of change of the field u at instant in time t, and I will assume that the equations of motion are such that only dependence is through the field t. And if you remember, for finite dimensional system, u was indexed, there was n components of it, but now it's getting indexed by x, by continuous parameter. So this is a functional of this function of u. But all it is this equation here that I've written out. So you know what it is. Invariance means that there is a set of abstract group elements to belong to some group, G, such that as I apply them to your equations of motion, and what I do is I apply it either to the field itself, and remember that has to be done as some representation of my abstract group element. So we'll have to think, how do we represent actions of a group? Invariance means that this law of motion for the field, in other words, symmetry conjugates form, in other words, symmetry commutes with it. And, if this is some dimensionality of state space, this function returns something in the same dimensionality. So it's the same representation acting on f of u. Now, because these are fields, you might scratch your head what this representation is. What I'll do is I will represent it computational in terms of computational degrees such as Fourier modes, and there we have no problem understanding what the symmetry does. So now you think of it just a little bit abstractly. So that's invariance. Now, in ring of fire, there are two obvious invariances. One is that we have one parameter group, which we call SO2, special orthogonal group in 2 dimensions. And what that does is I can define a group element. So we have group elements tau, and I'll parameterize them by L. By L I mean some kind of length, because I'm in this ring of fire, this is of length L, so little l is how far I rotate the ring in these units. Or you might find it more natural to use units over 2 pi. So all of these rotations, they form group G, which is in this case called SO2. And the way they act is that if I apply T of lambda to my, I don't know what's good, maybe I'll divide it by L so it's dimensionalized. Dimensionless parameters will be just an angle. If I apply it to my state, u at x at time t, I will get another solution, which is u x plus L at time t, where L is something that is 0 and up to L by periodicity. These are the same points. So it says if I have a solution, there is no orbit 0 point on this circle, so they're all equivalent to good. And the other that I have is a reflection And what reflection will do, it'll take U. So now that one is defined with respect to what I call x equals 0 point. So I'll have to think a little bit about that. But what it does is it takes a solution such that you flip where the x is. So you change the way you measure the angle and measure in the opposite way. But as this is velocity, this is length over time, it also flips U itself. It's not a scalar field, it's a component of velocity. And what you do is, if you don't believe me, you just stick at this equation and check that they're both invariants. And for this translation invariance, it was crucial that we had a periodic boundary condition. So it's not just the equation, but it's equation plus boundary condition that tells you what your invariance is. And this is all I know about the symmetries. I don't think there are any other symmetries of Kuramoto-Shivashinsky that are known to me.